Hey everyone, and welcome to This Explainer. Today, we're diving straight into the invisible mechanics of the world around us. Have you ever just stopped to wonder why everyday things behave the way they do? Like why ice melts, why wet clothes dry in the hot sun, or why a balloon actually expands? Well, it all comes down to the hidden nature of matter. We're talking about the invisible rules that completely govern our physical world. So let's zoom in and uncover what's happening right in front of us, just beyond what our eyes can see. Let's kick things off with a familiar scenario. Picture Mung Jose selling ice candy in the barangay. In the morning, that ice candy is rock hard, right? It perfectly holds its shape. But what happens if it sits out in the warm sun? It melts and turns into a liquid. But let's really think about this for a second. What is actually happening to the invisible particles inside that ice candy when it melts? Do they just disappear? Do they stop moving altogether? Actually, the microscopic truth is super fascinating. Those particles don't disappear at all. In the solid ice candy, the particles are packed tightly together, just kind of vibrating in place. But as the heat from the sun gives them more energy, something pretty cool happens. They don't get bigger, and they definitely don't stop moving. Instead, they gain enough energy to move more freely and literally slide past one another. And that newfound freedom, that's exactly what causes the solid treat to lose its rigid shape and become a liquid puddle. Moving through states of matter. Because, melting is really just part one of the journey. Let's see how these invisible particles keep shifting across different states of matter. Think about Anna hanging her wet clothes outside on a sunny day. A few hours later, they're completely dry. Where did all that water go? Well, it brilliantly illustrates evaporation. The liquid water didn't just vanish into nothingness. The water particles absorbed so much energy from the heat of the sun that they moved even farther apart, eventually escaping the fabric and floating into the air as a gas. Evaporation literally transforms that liquid water into a gas, scattering those particles right into the atmosphere. Let's test this concept out. Imagine a daily chore like cooking a pot of rice. You see that steam escaping from the vent of the rice cooker, right? Now, if we could put on a pair of magic microscopic glasses, how would we visualize that escaping steam? Are the particles tightly packed in a neat little grid, or are they doing their own thing entirely? If you guessed they're spread way out, you hit the nail on the head. Gas particles behave completely differently from solids or liquids. They are spread far apart, bouncing around randomly. Steam is a gas, and in that state, particles have so much energy that they don't just slide past each other anymore. They completely break away, spreading out as much as physically possible to fill whatever space they're in. And this exact same principle applies when a student blows up a balloon for a school activity. Ever wonder why puffing a little bit of air into a balloon makes the whole thing expand so evenly? It's simply because gas particles move freely in all directions. The wide spaces between them allow the air to spread out, push against the rubber, and fill the entire volume of the balloon. The danger of invisible gases. Now, understanding how these invisible particles behave isn't just some abstract academic exercise for a science test. It has serious, real-world applications that can literally save lives right in our own homes. Think about LPG tanks. A lot of families use liquefied petroleum gas for cooking every single day. But because it's a gas, what you can't see can absolutely hurt you. A tiny, invisible leak can turn into a massive hazard really quickly if you don't respect how gas behaves. Because gas particles are spaced so far apart and move so freely in all directions, leaked LPG doesn't just form a little puddle on the kitchen floor like spilled water would. It rapidly expands. It can fill the entire kitchen space completely undetected. And that creates an incredibly dangerous flammability risk, because that gas can easily travel across the room and reach a random spark or an open flame. Which is exactly why we have specific safety protocols. These practical reminders directly rely on our understanding of how gases expand. We have to keep the area well ventilated, so if gas does escape, it diffuses outside instead of building up inside. We always close the tank properly, check for possible leaks, and this is a huge one: never, ever light a fire if you smell gas. Understanding this invisible science is literally what keeps our families safe. Why scientists use models. Up until now, to wrap our heads around these invisible behaviors, we've been heavily relying on visual diagrams, which begs a really fascinating question. How do scientists actually study and explain things that are totally unseen? The answer is scientific models. Since we can't just look at atoms and microscopic particles with the naked eye, scientists build physical, conceptual, and mathematical models to represent matter. These help us visualize and predict how things will act. But it's super important to remember that a model is just a representation. Every single model has its own limitations because it's an approximation, not the complex real thing itself. The evolution of the atom. Okay, let's zoom in even further. Past the melting ice candy, past the steam, right down to the fundamental core of matter, the atom. It's amazing to trace how our scientific models of the atom have dramatically evolved over time as brilliant new discoveries popped up. We started with a simple, indivisible model, just a tiny, solid sphere that couldn't be broken apart. Then, as experiments got better, that morphed into the plum pudding model, and eventually it transformed into the highly sophisticated planetary model that we recognize in textbooks today. The plum pudding model was actually a huge breakthrough at first. It was the very first model to suggest atoms had negatively charged particles scattered around like plums in a pudding of positive charge, and it was super helpful for its time. But it had some pretty major flaws. It totally failed to explain the precise, highly structured arrangement of atomic charges that later experiments started to reveal. The model just had to change. Enter Niels Bohr. Bohr proposed a brand new, highly structured model credited for showing a positively charged core, the nucleus, smack dab in the center. And orbiting around that nucleus are negatively charged particles moving in fixed paths. It's called the planetary model because it works exactly like planets orbiting the sun in our solar system. Because of its incredible clarity and accuracy in explaining how matter interacts, this planetary model remains the most widely used and updated foundational model of the atom today. But honestly, here is the most exciting part. Science is this ever-evolving process of continually zooming in closer and closer, testing the boundaries of what we know. We went from a solid invisible ball to plum pudding to a literal miniature solar system. Knowing that our scientific models are constantly subject to updates and improvements as our technology advances, it leaves us with a pretty thrilling question. What entirely new microscopic truths about our universe are waiting out there in the invisible world, just ready to completely rewrite our models tomorrow? Keep questioning, keep observing, and thanks for joining me on this explainer.